Okay, in the previous class, we did a very important thing. We derived the one of the most popular form of adaptive filter called least mean square (LMS). Okay, it was like this: at any nth clock, there are three operations. First, filtering. You have got filter coefficients at nth clock as Wn vector, which is W0 coefficient, but a function of n, because they are changing from index to index because of the adaptation. So, filtering part is this Wn filtering part, it gives you yn by virtue of this. Xn is the input data vector. This you are familiar with, I have done it many times. So, filtering, then output error computation, En, which is difference between Dn. So, Dn is given to you during what is called training phase, during the adaptation phase. Okay. So, sample Dn is given and clock after clock you do this computation, and using this En and Xn you move from Wn to Wn plus 1. There is filter coefficient vector to be used at the next n plus 1th cycle. That is that LMS formula from Wn plus mu is the step size, very important parameter, Xn vector En scalar, end. You can start from n equal to 0 to some point final of your choice, and you can start with that initial condition W0 required, because n is 0 means W0 must be known, then only you can find W1. So, W0, any initial condition is fine, but normally we prefer 0 vector. This was LMS, and remember this was obtained from the steepest descent procedure by approximating odd by a so called quote unquote bad approximation. Bad approximation in the sense we just took it to be Xn into X transpose n, not averaging over many such matrices. This is a matrix Xn into X transpose. There could have been Xn minus 1 vector into X transpose and dot dot dot, and they added and averaged. That we are not doing. We replace this by this and P by just Xn dn. Okay. Because of these errors, and this part is called the gradient update, weight update part, weight and the next cycle update part. Okay. Because of these approximations, we pay a price. The weights do not converge absolutely to the optimal one, they converge in the mean, that is limit n tending to infinity. Wn was converging earlier to W opt in the case of steepest descent. Though we did not prove it, but from the graph we plotted, from the figure it was clear, it can be shown it converges directly. But in the case of LMS, it does not. But in the case of LMS, data vectors are random, because you see with Wn I am adding mu into Xn vector into En. So, En into Xn, En into Xn minus 1, En into Xn minus 2 and En again Dn minus Yn. So, all those are random. So, every clock I am adding a random vector component to current weight, and that is how Wn is generated by this process clock after clock, but that is also random. So, if it is random, if we take the expected value at any clock, so every point has some expected value, that will go to, sorry, this is not x, I am very sorry, this is W. That is, as I told, if you take a particular weight W k n, this is the corresponding optimal value, W k its optimal value. W k is random, so it might fluctuate like this, like this, like this, its average is here. After some time it may fluctuate here, then it may fluctuate here like this. But as it goes to very large index n, this n tends to infinity, it will be fluctuating around the optimal one. So, mean of the fluctuation will be W k opt. Then we try to minimize the range of fluctuation. So, it fluctuates in a small range around that optimal one, which will serve our purpose. Okay. That is controlled by mu actually, but that we will see later. This was LMS algorithm. So, this I have to now show how this happens, how this happens. I have to now show. This is my first goal. All right. So, at any clock I define V n as the weight error vector. This is the optimal one, this is the actual one at nth clock, this much is the error. So, this is the weight or coefficient, filter weight or filter coefficient, they mean the same thing, weight error vector. I want to make a substitution, I want to substitute W n by this everywhere, so that I get a corresponding equation in terms of V n, because I have to show that this error vector in some sense goes down. So, I do one thing, I subtract V n from left hand side, I subtract V n from right hand side, that will give me, sorry, I subtract W opt, I subtract W opt from left hand side, W opt from right hand side. So, W n plus 1 minus W opt will be V n plus 1, W n plus 1 minus W opt, W n plus 1 minus W opt, that will be V n plus 1. Right hand side W n minus W opt plus this. So, W n minus W opt is V n mu into x n E n. But this is not enough, because you know E n itself contains W n. This is how. What is E n? D n minus Y n, and Y n is W transpose n x n. So, here also I have to make substitution W n in terms of V n. So, W n is equal to V n plus W opt. So, that is what I will bring here. D n minus V n plus W opt transpose x n. All right. Now, here what I will do, mu x n, then there is one term V n transpose x n. V n transpose x n, you know, if I give you two vectors A and B, A transpose B, sorry, you know A transpose B is B transpose A. A and B are two column vectors. Okay, this is very simple. So, V n transpose x n, or maybe the whole thing transpose x n, I can write as V n or okay, V n transpose x n, that itself, V n transpose x n is same as x n transpose V n, and that I take out. So, I have V n plus mu x n minus, I am taking that particular term, mu x n into minus of x transpose n V n. So, it will be mu x n this one, and then V n transpose x n is same as x transpose V, A transpose B is B transpose A. So, it will be and other term is mu, sorry, mu x n, this one, minus d n minus w of transpose x n. Okay. This also I write as x transpose w opt. A transpose B is B transpose A using that. This also I write as x transpose n. Okay, W of transpose x n is same as x transpose n W opt. All right. This is actually output of the filter if I use W opt as the filter coefficient vector. So, this is the best filter's output error. It will have the minimum variance. X transpose n W opt or W opt transpose x n, they are same. That is the filter output. If I put W opt as the filter coefficients, W optimal, corresponding error which will have the minimum variance because I am using W opt. Okay. That error is given by this d n minus filter output. All right. So, I keep it as it is, and I can further write it this way. I take identity matrix, V n is identity matrix into V n, identity matrix into V n is V n itself. So, this is identity matrix into V n minus mu x n x transpose n V n. So, this V n again I take common. So, it is okay, and this much is as it is. Let me do one thing. Let me erase this bracket. X n d n minus again mu x n d n minus mu is common. So, x n is x n x transpose n W opt. This is what I have, and we all know W opt is R inverse P, right? W opt is R inverse P. So, we consider this second term. Now, if I cannot proceed any further, this is what I have done, and you can try very well, but you cannot simplify any further, you cannot proceed any further. You have to do something very new now, and then again doors will open, you can proceed further. That is, if I now take the expected value of the left, E of this, and then E of right hand side, then again new door will open, and let us see that. Expected value of V n plus 1 will be expected value of these I minus mu x n x transpose n outside V n. The expected value of I minus mu x n plus the other term mu x n d n minus x n x transpose n W opt. Expected value okay. Now, expected value of this xn into dn is by p vector, right. So, you can even work like this, E on this minus E on this. E on this much is p, by definition cross correlation vector between xn and dn, xn vector and dn. So, this is p, and here xn x transpose n, there is a matrix with random elements times w of is constant. So, you can as well apply E on this matrix first and then multiply by w of, you will get the same thing. Okay, that I have done earlier. So, E of this is R, xn x transpose n, that is autocorrelation matrix R, and then w opt. W opt we know is R inverse P, that is your W opt. So, R and R inverse cancels, I get identity to P is P minus P, this is 0. So, this is how the door opens if I apply E on it. So, at least one part gets 0, becomes 0 and it becomes simplified, all right. So, I carry on with this. Next, I got x, this term is the most complicated term, xn x transpose n. So, I got a matrix xn x transpose n. So, every element will be a product of one term, maybe xn minus k, xn minus I, and maybe another term xn minus j, that will give you ijth element times Vn. So, this is this matrix times Vn. So, what will happen, any row times this, that will be 2 terms of xn times 1 term of Vn multiplied, again added with again 2 terms of xn multiplied by 1 term of Vn, like that. Any row here, ith and jth, suppose this is xn minus I, xn minus j, and I am taking expectation of course, xn minus I, xn minus j, and when you multiply this by Vn, you will multiply this by Vn minus j. Okay, this will be the multiplying top guy, this the next guy, so Vn minus j, and this you keep doing for all the elements, this times this time, like that. Okay, this times this times this times this, and add it. So, every term will have 3 components, 2 multiplied from here and then further multiplied from 1 component from here. So, 3 and then expected value. Okay. Here we make an assumption called independence assumption. I will tell you later what is the basis of this. We assume Wn is statistically independent, this vector is random after all, I have told earlier, but this is statistically independent of xn vector. Okay. That means also Vn, which is nothing but Wn minus a constant W opt, that is also statistically independent Si of xn. Now, why statistically independent? Because if I now apply E, you remember one thing from our previous discussion on probability and random variables and all that. Suppose x, y are Si, statistically independent. Okay. Then, if you have got some function like f x g y, f x g y, then its expected value will be this into joint density, but joint density will be this because they are statistically independent, and then double integral dx dy, and you can take f x p x x under one integral, that will give you expected value of f x, g y p y y under another integral, that will give you expected value of g y. So, not only you have E of x y is E of x E y, it will be for any function f x g y, if you have anything that can be separated into one function of x, another of y, and take the expectation, because probability density also, joint density also is separable now, product of marginal density for x, marginal density of y, the whole integral you can separate out, okay, outer and inner integral, and that will give you the two expectations, E of f x, E of f y. But if they are only uncorrelated, this will not happen, because probability density, if I cannot break down into product of individual marginal densities, this cannot happen. Uncorrelated only means that expected value of x y is E x into E y. That follows from here also. If you have only f x equal to x, g y equal to y, x y, and this means x times g y, y times, so you get E of x, E of y. So, that I told that time, that in the beginning only, if they are statistically independent, they are always uncorrelated. But this does not follow if they are uncorrelated, because you must be able to break the probability density, write it as a product of individual marginal densities, one of x, another of y, and then only this happens. I want that here, because here I have got product of three terms, one term of x, maybe x n minus I, n minus j, and one of v n, expected value of that. It is not simply x and v. Then I could have 1 x 1 v and E of that. Then I could have applied uncorrelated assumption, and that would have been E of this x term into E of this v term. But here I have got more than that. Here I have got 1 x minus I, n minus j, and then one term from v. This product I have to apply E, and I want it to be separable. For that, this is required, statistical independent. Then I can have the overall expectation is an expectation of this part, okay, function of this x and function of y, so v. So, expectation of x n minus I, x n minus j, this part, and multiplied by expectation of the corresponding term here, v n minus j, v n minus v n minus j, okay, and so on and so forth for all the elements. So, it will be like E of the whole matrix, because I am applying E on every term. Okay, every term is a product of one x and one data of x and another data of x, x n into x transpose n. Okay. So, if it is ith row, x n minus I, and then x n minus j. So, x n minus I into x n minus j, that product, and ith row times this. So, this will multiply v n minus j. So, it will be x n minus I, x n minus j into v n minus j, expected value of that. Under statistical independence, if x parts, all the x terms and all the v terms are statistically independent, then it will be E on the components involving x only, like x n minus I, x n minus j, E of that multiplied by E of whatever data from whatever components I have from v n, in this case only one term. Okay. So, like I am putting E here, I am putting E here, and this I have to do everywhere. So, this will become then E of, so under this assumption, E of this matrix and V n, it will be separable. And this is my good old autocorrelation matrix R, this is E V n. So, E of I into V n is V n, E of V n minus E on this, which is R, into E of V n. So, this will become, this will give rise to this. I as it is minus mu, this part will give you R, this R, and E of V n. I into E of V n is E of V n, and that is what I have here. E of I V n, that is V n. So, E of V n, I into E of V n, E of V n minus mu E on this part because of statistical independence. So, E on this part is R as I told you, and E on this part E V n. So, take E V n common, it is this. Okay, very simple equation. With this I move to the next page. I am rewriting what I obtained there. Okay. E V n, the moment we apply E, then the result is no longer random, okay, it is constant. It may be a function of n. So, let me call it V prime n, this vector. It is not random, no function of n, and then it is V prime n plus 1. All right. This I do. Another thing we have seen, R is a Hermitian matrix, autocohesion matrix, and we can write it like T, D, T, H. I did it extensively, very elaborately in one of my lectures, where T is unitary, means T H is the inverse of T, T H T, and if T H is the inverse, you can also have T T H, both is identity. So, T H is the inverse of T, T is the inverse of T H. So, T is unitary. Basically, all the columns are the orthonormal eigenvectors of R, and D diagonal matrix, each diagonal entry are an eigenvalue of R, but R is Hermitian, so they are real. So, I now have a much simpler equation. V prime n plus 1 is I minus mu R V prime n, and R I will replace like this. Okay. So, in the next section, next stop, I will complete the proof. Thank you very much.